Okay, so we are going to do numerical type questions of this year's advanced paper. Okay, and this is paper 2. So let us see then question number 9. What is given here? What is given here? We have a solid sphere of radius r and it is carrying a charge q. Total charge is q. The sphere is rotating about an axis passing through its center with an angular speed omega. The ratio of magnitude of magnetic dipole moment, to the angular momentum, we have to basically find this thing, magnetic dipole moment by angular momentum. From there we will get the answer. Okay, so we have a formula for this, and that formula is magnetic dipole moment by angular momentum q by 2m. So it looks like answer should be just one, right? But there is a problem. What is the problem? The solid sphere is conducting in nature. That means all of the charge will come on the surface, while all the mass is not going to come on the surface. Okay, so this formula is not valid. Okay, this formula is valid only when charge and mass are distributed in a same manner, distributed in the same manner. What is the meaning of this part? Suppose we have a solid non-conducting sphere. Okay, solid non-conducting sphere. So mass is also distributed all over the body, and charge can also be distributed all over the body. Okay, so in this case this formula will be valid. Okay, but we have solid conducting sphere. Okay, so what will happen here? Mass is distributed all over the body, mass is present all over the body, but charge is only at the surface. We know that these charges will repel each other. Here also charges are repelling each other, but they cannot move because the sphere is non-conducting. Here the sphere is conducting, so charges will come at the surface. Okay, so it looks like we cannot use this formula, but what we are going to do, we are still going to use this formula. Okay, how? Here charges are coming at the surface. Let us assume that all the mass is also coming at the surface magically. Okay, if let us find the magnetic moment of a hollow cell. In hollow cell what happens? Charge is also at the surface, mass is also at the surface, so we can use this formula. Okay, so U by L hollow, mu by L hollow, it will be given by formula Q by 2m. Now, so mu will be Q by 2m into angular momentum of the hollow sphere. HS means hollow sphere. Okay, now mu by solid sphere, but we actually had to find what? Mu by angular momentum of the solid sphere. So it looks like it will be easy. we just have to divide it by whatever we have found, we have to divide by angular momentum of solid sphere, right? So what will happen now? Q by 2m, and this angular momentum of hollow sphere, see, masses are same, radii are same, but only difference is that it is hollow, it is a shell, and it is a solid sphere. So for hollow sphere it is 2 by 3 m r square into omega, and for the solid sphere, why 2 by 3? Because it is the moment of inertia, okay? And for the solid sphere it is 2 by 5 m r square into omega. So clearly we will get q by 2m, and this 5 will go on the top and 3 will remain at the bottom. So 5 by 3. So our answer is 5 by 3. Alpha is 5 by 3. So alpha is equal to 5 by 3, 1.67. Okay, that is our answer. Now we are going to the next question. Okay, it is extra page. Okay, next question, it is slightly difficult, okay, and I was not able to do in the first attempt, okay. So let us see, and there is some confusion also. After doing this question also, we have some confusion. So we have a hydrogen atom, and it is initially at the ground state. Some photon is just striking it. Photon's frequency is given. It will have some energy E1 given by this formula. Okay, Planck constant into the frequency. Okay, and it ejects the electron with a kinetic energy, and this photon is able to eject the electron with a kinetic energy 10 electron volt. So basically this photon is first ionizing the hydrogen atom and then giving the electron a kinetic energy of 10 electron volt. So looks like this photon have energy how much? First of all, to ionize the hydrogen atom, you require 13.6 electron volt, plus you are giving some kinetic energy also. It is giving kinetic energy to the electron also, and that kinetic energy is 10 electron volt. Okay, got it? So we will need this thing in the question, so that is why I am doing it. Okay, so first E1 is 23.6 electron volt. Now what is happening? This electron which have 10 eV energy, it is striking a positronium ion. Positronium ion means it is just like electron, but it has a positive charge. Its mass is same. It is also given. Okay, they have talked about positronium ion. Okay, and now what happens? It is getting, we are getting a positronium ion, and let us combine it first. Now first of all, I want to say there is no string or rod here. Okay, I am just trying to show a bond. Okay, there is nothing in between. Okay, so this is our electron and this is our positronium. Okay, okay, positronium ion, and what they are saying that the center of mass, this center of mass is moving with a kinetic energy 5 electron volt. It is given in the question. Okay, what is happening? This resulting positronium atom moves with a kinetic energy of 5 electron volt. It is given that positron have same mass as that of electron. Okay, we discussed it. And positonium atom can be considered as a Bohr atom. Okay, now this is a Bohr atom. Okay, and Bohr atom in which electron and positron orbit around their center of mass. So this is our center of mass, and this is rotating like this. Okay, and electron is rotating like this. Okay, so they are both rotating, orbiting, actually orbiting around their common center of mass, and the center of mass is moving with 5 electron volt. Okay, wow. So it has 10 electron volt. What happened to the extra 5 electron volt? Okay, we will talk about it. Considering no energy loss, no energy is lost in the process, the difference between two photon of energy. So here one photon is also emitted. Okay, and that photon, it's okay, yeah, this photon has a energy given by this formula. I will call it E2, and actually we have to find E2 also. Okay, so what is happening, we had total 10 electron volt of energy. Out of 10 electron volt of energy, we have E2, energy of the photon, and kinetic energy of the atoms. Kinetic energy, because atom center of mass of the atom is moving with some velocity. Now apart from this kinetic energy, it will have some rotational kinetic energy, Ke rotational. Okay, and apart from this rotational kinetic energy, it will have some, instead of K rotational K, I will write just K. Okay, and apart from this, it will have some potential energy also. Why potential energy? Because earlier this electron and this positron were were at a large distance. Now they are at a smaller distance. They have a potential energy also. So it looks like no mass is lost, no energy is lost. Okay, so it looks like both side energy will be same, and basically we have to find E2, and then we have to find the difference between E1 and E2. What we have to find? The difference between two photon energy. Okay, so this was slightly complex question, and what they are saying, Bohr's model of atom is valid. Okay, so Bohr's model of atom is valid. So let us go to the next page. So Bohr's model of atom is valid. So angular momentum will be nh by 2 pi, right? Angular momentum. Okay, one more thing, they are talking about the ground state. So n will be 1. Okay, but anyway, angular momentum is nh by 2 pi. So what is the angular momentum? Is it mvr or mvr by 2? Let us see. So it will have some velocity v, and it will also have some velocity v, because masses are same, velocities will also be same. So, and if this distance is r, then distance from the center will be only r by 2. Okay, so angular momentum of this particle will be mv r by 2. Angular momentum of this particle will also be mv r by 2, and both are in the same sense. Okay, both are orbiting anticlockwise as per our figure. Okay, so what we discussed here, angular momentum of the positron was mvr by 2, and angular momentum of the electron was also mvr by 2, and it is equal to nh by 2 pi. n here is 1, but let us write it. Okay, so one formula we already got, and it is similar to what we had in the Bohr's model, right? Now another formula, because we have two unknowns, v we don't know and r we don't know, so we have two unknowns, so we need one other equation also, and other equation comes from that for the orbi for the orbiting body we need some what they call it, centripetal force. Yes, for the orbiting body we need some centripetal force, and this comes from the electrostatic attraction. So whatever centripetal force is needed for orbiting the orbit, it is given by electrostatic force. So the centripetal force will be mv square r by 2. Okay, now there is a problem. Why r by 2? See, radius of the circle is only r by 2. Okay, distance between them is r. While calculating electrostatic attraction, we have to use r, but while calculating the centripetal force we have to use r by 2. So I will write this thing, 1 by 4 pi epsilon naught e square. Both charges are e, one is plus e, one is minus e, so this is the force of attraction. I am not writing a minus sign. Okay, and here I am writing just r square. Okay, so what does it look like? One of the r will cancel out. Okay, and we will get this equation, mv square r, this 1 by 2 will go that side, and it will become 1 by 2 1 by 4 pi epsilon naught e square. Okay, now what is happening? This r has gone this way. What is happening? This looks similar to what we got in Bohr's model, only difference is this factor half. So let us see. So mvr, this kind of calculation we do in Bohr's model. Okay, half 1 by 4 pi epsilon naught e square. This kind of calculation we do it in Bohr's model. So here, okay, actually it is v. Okay, v is present twice. Okay, r is present only once. So v will be 1 by 2 e square by 4 pi epsilon naught, and this mvr, what is this mvr? This mvr will come at the bottom, right? This mvr will come at the bottom, and mvr here is nh by 2 pi. So nh by 2 pi, 2 pi will go on the top. Okay, so it looks like you will get 2 here, and v will be 1 by 2. V will be 1 by 2 e square 2 epsilon naught nh. Now one more thing, why I have kept 1 by 2 alone, not with the other things, because this is actually v naught. What is v naught? V naught is the velocity of electron in ground state in Bohr's orbit. Okay, velocity of ground state electron in Bohr's orbit. For hydrogen, z is 1, and okay, for ground state n is 1. So I will write v naught by 2. Okay, so it is v naught by 2. So once we found v naught by 2, let us find R also. Sorry, we found V in terms of V naught. Let us find R also. So what will happen to R? MVR is equal to NH by 2 pi. Now see, in Bohr's model and in this model, equations are same, but this V is half. V is half of V naught, so R will be double of R naught. Okay, here equation. Okay, here V is V naught by 2, so R will be 2 R naught. Okay, because we want this product to be same. So one quantity is halved, other quantity is doubled. So we found R, no, R also. Now we are going to calculate the energy. Now we are going to calculate the kinetic energy and potential energy. How to calculate the kinetic energy? For kinetic energy, we have two things. One, we have electron, and mass of the electron is half m v naught by 2 the whole square. Okay, but we don't have just electron, we have a positron also of the same kinetic energy. If you calculate it, k will be half mv naught the whole square. So k I am getting is k naught by 2. Okay, so k value I am getting it k naught by 2. What about u value? Let us see. 1 by 4 pi epsilon naught e square by 2r. Okay, u square by r, but don't forget a minus sign. Okay, now this r is two r naught. So what you can see that if r is doubled, u will be half of, if r is doubled, u will be half of u naught. Okay, so what is u naught? U naught is the potential energy of electron and hydrogen nucleus in the ground state. Okay, and here u is the potential energy of the combination of positron and electron, so it is also half. So it looks like our problems become easy. Okay, so uh, this u plus k, this u plus k will be u naught by k naught, u naught by k naught by 2. Now one thing, this u naught by k naught, it is the total energy, total energy, potential plus kinetic energy in ground state for hydrogen atom. Okay, and we already know that, we know this value. Okay, this value is minus 13.6 ev. Actually we have used this also, so this will be minus 6.8 ev. Okay, now we have found this. Now now we are in the last stage, so let us go to the problem. Let us go to the problem. Okay, here I have written things. I will make the figure again. Okay, because everybody forgets. So what happened? We had 10 electron volt of kinetic energy. We have okay, I will write final energy is equal to initial energy. Final energy, no, initial energy is equal to final energy, no problem. It is the same thing. Initial energy is equal to final energy. We will use the energy conservation. Okay, so in initial energy was only 10 electron volt, and in the final energy we have so many parts. One is kinetic energy of the atom, translational kinetic energy. Other is k naught k rotational plus u plus E2. E2 is the energy of the photon. So what happens? What happened? Let me explain. It is the total kinetic energy of the electron. Okay. Now electron is hitting the positron. It is making a positronium ion, and translational potential energy is translational kinetic energy is phi BB. This part is phi BB, and we have some rotational energy also, and electrostatic potential energy also. Some of those energy we just found minus 6.8 ev. Okay, and E2 we have to find. Okay, E2 we have to find. So what will be E2? E2 will be 10 minus 5 plus 6.8 ev will be E2. We just found E2 to be what is it, 5 11.8. Okay, and E1 minus E2, we have to find this thing. Okay, this E2 is energy of the second photon, and this E1 is the energy of the incident photon. Okay, so energy of the incident photon was 23.6 ev. Energy of the emitted photon is 11.8 ev. So we are getting 11.8 ev. Okay, so this solution, I have some confusion also. Okay, I will talk about that. Okay, but I will not go that way. Here in Bohr's model, only electron is orbiting, nucleus is at rest. Here electron is also orbiting, and the positron is also orbiting. Okay, and we are taking the sum of angular momenta of both things. And in the Bohr's orbit, we have taken the angular momentum of electron only. Okay, so because of that thing, answer may be different. Okay, let us see what IIT provides as key. Okay, for now I am going with this solution. Okay, these are actually hypothetical questions. Okay, now this is the next question. This question will be slightly easy. Okay, we have an ideal monoatomic gas n moles. Okay, and they are taking through a cycle, and cycle starts from W, goes to X, Y, Z, and returns to W. Okay, okay, and they are adiabatic and isobaric quasi-static process. Okay, they are either adiabatic or isobaric. Okay, so let us see which one is adiabatic and which one is isobaric. Here you can see that V proportional to T means what is it? V proportional to T means isobaric, right? Isobaric. So this process is also isobaric. Okay, this was easy to find, and obviously these two processes will be adiabatic because it is given. But let us see what happens in adiabatic process. In adiabatic process, pv to the power gamma is some constant. Okay, before going ahead, let us read the full question. Okay, the volume of the gas at different point it is given. Okay, 64, 125 and 250 centimeter cube. If the absolute temperature of the gas, here temperature is given, temperature at W is given. Okay, and such that nRTW is 1 joule. Okay, nRTW is 1 joule. Okay, we will need this thing, where R is the universal gas constant. Then amount of heat absorbed along the path xy. Okay, so this is the isobaric path. Okay, this is the isobaric path, and we have to find the amount of heat absorbed along this path. Okay, so let us confirm these are adiabatic or no. Okay, actually we will need it. Okay, so because we don't have PV diagram, we have TV diagram, I would like to eliminate T here. Okay, sorry, P here. So P will be nRT by V to the power gamma is equal to C. So power of T is 1 and power of V is gamma minus 1. This is minus 1 power. Okay, it is at the bottom. So this is minus 1 power. So, and this will be equal to some other constant. Let us say C1. Okay, let us C1. So you can see that power of V is still positive. Because gamma is more than 1, so power of V is still positive. So one thing increases, other thing will decrease. One thing increases, other thing will decrease. So here temperature is increasing, volume is decreasing. Here volume is increasing, temperature is decreasing. So these are these are adiabatics. Okay, so this is also adiabatic and this is also adiabatic. Okay, these two things are adiabatic. Okay, and what we have to find, the amount of heat absorbed by the gas along x to y. So basically what we have to find, delta q x to y. Okay, what kind of process is x to y? Okay, it is isobaric. So I will write isobaric also. Okay, so amount of heat absorbed by gas in isobaric process is ncp delta t. Delta t means final temperature. Final temperature means temperature of y minus temperature of x. So basically n is n, p is for monoatomic gas. What is cp? For monoatomic gas, cp is 5 by 2r and tw minus tx. So basically what we need to find, ty and we need to find tx. Okay, so, and we will need the difference of these two temperatures. Okay, so what is ty? From here we will not do it. Okay, let us go from x. Let us find tx. We will see this process. This process is adiabatic. For this adiabatic, for the adiabatic process, we have this equation. Okay, so I will write this thing: T W V W is equal to Tx Vx to the power gamma minus 1. And we have a good news. Tw. Okay, so answer uh, okay, we actually need the temperatures in the terms of TW, so we have no problem with TW. Okay, so this will be VW by Vx to the power gamma minus 1 is equal to Tx. Okay, now TW, we don't have any problem with TW. Okay, and VW by Vx, VW by Vx, it can be easily found. Okay, it is given. Okay, VW is 64 and Vx is 125. So VW is 64 and this is 125. Okay, and power here is 5 by 2 minus 1. 5 by 2 minus 1 because gamma value is 5 by 2 is equal to Tx. So it looks like I can complete the problem here. Okay, in the first page. So Tx is TW 64 by 125, and this is 5 by 2 minus 1. 5 by 2 minus 1 is 3 by 2. If you take the cubic root, no, uh, 3 by 2. Okay, oh wait, gamma minus 1, oh sorry, gamma is we are doing some mistake here. Okay, gamma here is 5 by 3. Okay, gamma is not 5 by 2, it is 5 by 3. Okay, sorry about it. So this power will come to be 5 by 3 minus 1, it will be 2 by 3. It will not come 3 by 2, it will be 2 by 3. So if you take the cubic root, you will get 4 by 5, and if you do the square, you will get 16 by 25 TW. We already got one of the temperature in terms of TW, right? What about Ty? Because we need Ty also. It will be easy because this is isobaric process. Okay, so it is changing proportionally. So Ty will be just 2 times of Tx. Why I am writing it? Let us see the data. Okay, see, volume at X is 125 and volume at Y is 250. So volume is just doubled. If the volume is doubled, temperature is also doubled. So Ty is double of Tx. So I will write 1632 by 25 TW. Now we are going to substitute it here. Okay, now we are going to substitute it there, and I will use red color. Okay, so n is n, r is r, 5 by 2 is 5 by 2, and Ty is 32 by 25 TW, and Tx is 16 by 25 TW. If you do the calculation, you will get NRTW 5 by 2 into this part will become 16 by 25. Okay, NRTW is given 1 joule. Okay, it is given in the problem, and then what we are getting, this is 5, this will become 1.6. So our answer is 1.6 joule. Okay, our answer is what? 1.6 joule. 1.6 joule energy was given. Okay, so that is our answer. Now let us go to the next question. Okay, this question, okay, it is slightly easy because this kind of question actually we do in the classrooms. Okay, so we have earth here. Okay, okay, let us make earth spherical. Okay, we have earth here, and from earth we have a geostationary satellite. Okay, we have a geostationary satellite, and it is moving with an angular velocity omega is equal to 2 pi by 24 hours. Okay, and what they are okay, so we have a geostationary satellite above the equator, and it is orbiting around the earth at a fixed distance r1 from the center of the earth. We have a second satellite also which is orbiting in the equatorial plane in the opposite direction. So basically, if this is coming down, sorry, if this is going this way, our other orbit, our or other orbit r2 is more or less, r2 is a smaller. Okay, so basically r2 is a smaller. Second satellite is orbiting this way. Okay, and this r this r2 is this r2 is r1 by 120 1.20. This r2 is r1 by 1.21. So basically second orbit is smaller, it will rotate faster, its time period will be less than this time period. Okay, let us call this time period t1. Okay, now, and they are orbiting in the opposite sense, and what we have to find the time period of second satellite is measured from the geostationary satellite is 24 by p hours. Okay, so basically we need to find the time period of this satellite with respect to the geostationary satellite. So it looks like first we have to find the angular velocity of this satellite also, or time period of this satellite also, then we will do our calculation. Okay, so time period t2 by t1 can already found using this formula, right? Okay, this is Kepler's law. Kepler's law is valid. Kepler given the law, a law for planets and sun. Okay, but it is valid for circular orbits also. It is valid for earth and its satellite also, or any other massive body and its satellite. So r2 by r1 is actually 1 by 1.21, and if you do 3 by 2 power, first let us take the square root. If you take the square root of 1.21, you will get 1 by 1 by 1.1, and if you take the cube root, okay, this kind of calculation actually we do. Okay, math people uh, discuss this like a trick. Okay, okay, so basically t2 is, what is t2? T2 is t1 by 1.331. Okay, now see, we have to find the T equivalent, okay, T relative, okay. So let us find omega relative. Omega relative will be omega 1 plus omega 2. Okay, relative velocity we subtract. Basically, we are subtracting because they are moving in the opposite sense. Okay, so effective angular velocity will increase. Okay, so 2 pi by t will be 2 pi by t1 plus 2 pi by t2, and 2 pi you can cancel out. Okay, so t will basically become t1 t2 divided by t1 plus t2. Okay, and I think this kind of formula people do it in classroom during the preparation. Okay, so t1 is t1 is actually 24 hour, and t2 is 24 hour divided by 1.331. t2 is a smaller. Okay, second orbit, second satellite is at a smaller distance, so it will run faster, its time period will be smaller. So and 224 hour plus 24, okay, you can write HH 24 hour by 1.331. Okay, so when you do this calculation, you can see that one of the 24 hour is gone. Okay, no need to do it, write it. So you will get 24 hour divided by 1.331, and this will become 1 plus, sorry, 1.33, 1.331 plus 1 by 1.331. So these two things are gone, and what we are getting at the bottom is 24 hour by 1 plus 2.331. Okay, so this is our answer. Okay, this is our p is equal to 2.331. Okay, so this p we have to find. Okay, 1.33, sorry, 2.331. Okay, so 12 number question we did. Let me see how much time we had. Okay, so it is almost 48 minutes we already recorded. Okay, now let me see the next question. Okay, 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 let us do it. The left and right compartments of a thermally isolated container of length L are separated by thermally conducting movable piston of area A. So this piston has a area A, and this is thermally conducting, means it will allow the passage of what, heat. So temperatures both sides are going to be same. Okay, and area is a cross sectional area A. The left and right compartment are filled with 3 by 2 and 1 by 2 mole of gas. So this side N1 is 3 by 2 mole and N2 is 1 mole. Okay, left and right. Okay, so left side it has more number of gases. Okay, in the left compartment, the piston is attached with a spring within spring constant K and natural length 2L by 3. Okay, so L naught here is 2L by 3, 2L by 5. Okay, sorry, 2L by 5. Okay, in thermodynamic equilibrium, the piston is at a distance L by 2 from the left edge and the right edge of the container. So basically this is also L by 2 and this is also L by 2. So basically both have the same volume, they will have same temperatures also, but one is containing more number of mole, so pressure here is high. More number of moles, more pressure. But how can be pressure be more? Okay, this is handling extra pressure, this spring is handling the extra pressure. Okay, okay, so this part we read. Under the above condition, if the pressure in the right compartment, here pressure is K L by A alpha, then we have to find alpha value. Okay, so basically right compartment pressure is given, we have to find the left compartment pressure also, and we have to see the difference in pressure. Here pressure is large and this extra pressure is given by this spring. Okay, this spring is applying a force. Okay, so let us see the equations. Okay, so for the left compartment, LC means left compartment. Okay, for the left compartment, N1 RT by is equal to PL. PL. Okay, V. Okay, V, for V I will write A L by 2. Okay, because volume is given in terms of area and length, so I will use it. Okay, no problem. So N1 is 3 by 2, R is R, T is T, PL we don't know, A L by 2. So what we are getting, this 3 will get out. Okay, and PL into A will be equal to 3RT by L. This PL into A is actually force exerted by left side of the gas. For pressure into area, what is it? Force exerted. Okay, now let us find let us find PR. Okay, for the right compartment, I will write PR, pressure on the right side, volume of the right side into the number of moles on the right. Number of moles on the right side is only 1. Okay, and temperature is T. Okay, so PR into A, PR into A will become okay, 2RT, 2RT by L. Okay, now what is happening? Let us write the force equation. Okay, now what is happening? From the left side, force is large. From the right side, force is a bit smaller. Okay, only 2RT by L. So this extra pressure, the difference of this force is handled by this spring. Okay, so this force, okay, and Kx, I will call it F1, I will call it F2. Okay, so let us write the equation. F1 F2, F1 is equal to F2 plus kx. And what is x? X is the elongation in the spring, and x in the is the elongation is in the spring. We can easily find it. Okay, x will be natural length. What is the natural length? Okay, x is the final length, which is L by 2, by from minus natural length of the spring. Okay, let us see what I have done here. Final length of the spring is half of L. Okay, and natural length is 12 by 5. So this is the elongation. Okay, if you calculate it 0.5, 0.4, you will get 0.1. Okay, 0.1 L. Okay, now from here F1 is 3 RT by L, 3 RT by L, and F2 is 2 RT by L. F2 is 2 RT by L, and Kx, K and X is L by 10. X is L by 10. So we actually need to find pressure, this pressure P in terms of KL by A. Okay, so from here let us find RT by L. Okay, KL by A. Okay, sorry. What we get here, 3 RT by L minus 2 RT by L, it will be RT by L, and that side was KL by 10. This is what we get. Okay, RT by L, KL by 10. Okay, now P value means PR. PR was 2 RT by L. Okay, I will write this equation. Okay, PR into A is 2 RT by L. We have a equation PR A by PR is RT. Okay, I am forgetting what I have written. 2 RT by L. Okay, PR into 2 RT by L. Okay, and PR is actually P. Okay, it is given in the problem 2 RT by LA. 2 RT by LA. Okay, now RT by L is what? This part we just found KL by no. Forget to. So 2 is to RT by L. This RT by L is KL by 10, and A is A. So we are getting 0.2 KL by A. Actually the question was easy. Okay, but there we have just some manipulations. Okay, so our answer for alpha is 0.2. Okay, so alpha is equal to 0.2. Okay, so that is all. Okay, I am ending it.